Hi, this is Josh with the support video for lesson number 19, SAT on volume. As you can see here in the lesson on the first page, states volume is the amount of space in solid geometry. The basic unit of volume is the unit cubed. Learning to compute the volume of basic shapes using real-world applications is a useful everyday skill. Volume is a part of our consumer culture. We buy things based on our needs for certain sizes of designs. We'll lower some basic solids. So in getting this lesson ready for you, here are the basic shapes that are most common among SAT level problems. And you should be familiar with these shapes for the exam. First one is the cube. V equals S cubed, the side length times itself 3 times. The next is the rectangular prism. Volume is length times width times height. The square pyramid, 1/3 side squared times height. Cylinder, volume is pi r squared h. The cone, volume is 1/3 pi r squared h. And the sphere, the volume is 4/3 pi times radius cubed. Just a quick way of getting used to these formulas for the volume that the space that they contain. Let's look at 3 of these 6 here, looking at the base shape. So the cube is a special case of the rectangle prism where the length, width, and height are the same number of units. But in mapping out the volume of the shape, you can take the base shape, which would be a square, side times side, and then multiply it by the height. So it's the base area raised to a uniform height. So that's why we have the formula side times side times side, or side cubed. For the rectangle prism, the length and the width are the base shape, which I've highlighted in blue. Then it's raised to a certain height, so we have the formula length width times height. I mention this because the cylinder is the same thing. Here we have a column. The base shape is not a rectangle, it's a circle. So it should make sense that we start with the base shape. A circle is pi r squared, and then multiply it to raising it up to a certain height, depending on how high the cylinder is. It could be the height of a soup can, or it could go all the way up like the column of a building. Volume is pi r squared h. The next type of volume formula is related to this idea of the base shape. For pyramids and cones, here the pyramid has a square base, so the area is highlighted in orange as side squared. That's a square. And we'll multiply it by the height, which is represented by the pink arrow, the height at the center of the pyramid. Remember, pyramids and cones are raised up to a single point. They're not raised up to a uniform level. And for reasons, the derivation we will not go into in this lesson, you need to know that it's 1/3 of the base times the height. In other words, a square pyramid, if we were to scoop up sand with our square pyramid, 3 scoops would fill up the cube on the left. It's really the same formula. If the height is the same as the side held on here, then we'd have side squared times side, but times 1/3. So if the height is the same as this cube, for example, 3 of these scoops of sand would fill up the cube. The volume is 1/3 the base area times the height. Similarly, the cone is related to the cylinder in the same way. The base shape is a circle, but we're raising it to a single point. If the radius and the height are the same for both the cone and the cylinder, in other words, if we were to scoop up sand, for example, or a material with the cone, 3 scoops of the cone would fill the cylinder to the top. The volume of the cone, again, is 1/3 pi r squared h. Lastly, for the SAT is another function here, the volume for a sphere. Here, again, for the derivation we will not go over in this class, we have 4/3 pi times the radius cubed. So remember, for these shapes, pyramids, cones, and the sphere, there's this additional fraction which stands in front of the remainder of the formula. Pyramids, cones, and spheres. So those are the 6 basic shapes for volume problems as you get ready for your SAT. Let's look at a few examples. And again, you should see these if you download the lesson, if you're enrolled here at Chang Learning. We'll go over 3, maybe 4 basic examples of volume problems as presented on the SAT. Example 1. A cardboard box is 8 inches by 12 inches by 3 inches. A cereal company fills the box only up to 10 inches in height. What is the volume of the cereal contained in 10 boxes? Well, the solution here is the volume of the single box, 8 by 12 by 3, we have to figure out how do we orient the box on the table so that we can then fill it with cereal. Well, thankfully, there's only one orientation that's possible. Since we're filling the cereal to a height of 10 inches, we have to have the height as 12, as I've drawn here with the pink arrows. Otherwise, the cereal will overflow in the box. Knowing this, we can then space out what the company is doing when they fill their cardboard boxes with cereal. They fill it up to, say, that orange line there, which is a height of 10. The rest of the box is just empty space, packing space. So the volume of cereal that's present in that box that you buy, that's 8 by 12 by 3, is really 8 by 10 by 3, or 240 inches cubed per box. Since we have an order here for 10 cereal boxes, multiply that by 10, and the total volume is 2,400 cubic inches of cereal. Example 2. What is the volume of a cylinder-shaped metal juice can with radius 3 and height 8 inches? Well, here it's drawn on the right side, and we want to know the volume that could be contained if the cylinder were filled from its base all the way up to the top. Well, we are given the variables in the reading. The radius is 3 and the height is 8. Just make sure that you know the formula, pi r squared times the height. And we'll have pi times 3 squared times 8. And 9 times 8 is 72. And the correct answer is 72 pi units of juice that can be contained in the juice can. Example 3. A cone sits atop a cathedral tower with radius 5 meters and height 36 meters. What is the volume of the space? Okay, so they give us the radius and the height, but looks like it says a 12 on the right, so I need to fix that. Oh, here, I fixed it here. So the height is actually 36. It's a very tall tower, and therefore the lateral height of this cathedral tower, like sits on the top of the building, would be 36.34 and not 13. All right, to find the volume of the cone, we have a third pi times the radius squared, so that's 25, times the height of 36. Well, a third of 36 is 12, and then 25 12s is the same as 300s, excuse me. So the correct answer is 300 pi for example 3. Moving on, next we have example 4. A sectional sofa is designed as shown on the right. Each cube is 2 feet on each edge. What is the volume of this sectional sofa? Well, if you haven't seen these, they can be made out of fabric or foam, but they're cubes that you can link together with either Velcro or with a strap, or they just click together, these modular furnitures. So one way of counting the amount of volume for each of these 2 by 2 by 2 cubes is to do the front, middle, and back of the item. Here I have it in 3D, and I think I used GeoGebra or Desmos to draw the cubes here, which would be the 2 foot cubes here in the front, on the up front left and front right. And then the next layer would be the mid layer. The seatings here, there are 5. And then what would be like along the back wall, we have 5 there, but it's 2 units high. So we have 10 cubes on the back wall. Adding them all together, that would be 17 cubes. 2 plus 5 plus 10 is 17. And multiplying that by 8, we get a volume of 136 units cubed. That was 2, 5, and 10. as you see with these pink arrows, counting the cubes in the sofa. Something that's really important for these three-dimensional problems is to sometimes have more than one way to find the sum. So again, if we start on the left and we go left to right, there are 5 sections here within these seats. So you can see that this L-shaped piece, that's 4 cubed from the far left. There's a little wedge here that's made up of 3 cubes. Here in the middle section, also 3. Here in the fourth section, also 3. And then the left and right are bookending here. They're the same design. So you can see there are 4 cubes that make up the sofa design in the end. So adding up those numbers for the cube count, 4 plus 3 is 7, plus 3 is 10, plus 3 is 13, plus 4 also gives you a total of 17. So it's nice to do the math in more than one way. Here we're using our spatial kinetic awareness. We're going along one axis to count, but you can also check that answer by going along another axis and counting the cubes. Other students said, yes, you could also do it as like first floor and second floor. And if you do that as well, you'll count 12 cubes on the first floor, plus an additional 5 cubes that are on level 2 above. It'll still total 17. Well, I hope this video was useful to you as an introduction to this lesson. Good luck with the problem sets and as you get ready for your SAT. Thanks for watching my video.